Well, good morning, everyone. Welcome. This is our, I believe, ninth edition of our virtual learning series that we started back in I believe, March now. So we're excited to have a good crowd here today, some familiar faces. And our topic today is getting to zero energy buildings. My co-presenter is going to be Alan May, who's a building analyst here at Cyclone Energy Group. He's going to be sharing the workload here with me today. We're going to start by talking about the worst building you can build by law, which is the building defined by energy code. And, you know, we've got people here from around the country, we've got people from around the world, and energy codes vary throughout different jurisdictions, obviously. But here in the United States, most all of them are based in the workings of ASHRAE Standard 90.1. And ASHRAE Standard 90.1 came out in 1975. It came out of the Middle East oil embargoes, and the need for energy efficient buildings became a very important thing with the cost of energy rising so much. And so the standard arose, and it really sat pretty stagnant until the late 80s, when it kind of started taking an overhaul and started to move in a forward projection. And it's taken some pretty giant leaps exponentially since then. Really starting in the late 90s, the standard moved to kind of a rolling, every 3 years it was updated. And with that, the components of that started getting greater. So those of us in the design community and construction community have witnessed this firsthand, that every 3 years, it seems, we have to learn a new set of efficiency values to specify into our drawings and into our designs. And, you know, the codes aren't, this is a graphic that ASHRAE put out in their 2020 plan, which obviously we're in 2020 now, so I guess they're living this. But a lot of people have projected a 2030 challenge, zero energy goal. I will have a big point of clarification. You see net zero a lot in these graphics and slides. ASHRAE and the Department of Energy switched from calling things net zero to calling them zero energy a few years ago. So, but the publications haven't really been updated yet in most things that are out there on zero energy buildings. But the projections are that a lot of people are going to try to design to zero energy buildings by the year 2030. ASHRAE is going to, you know, follow in suit, is pushing their codes to do that. Now, they're not pushing their codes to be zero energy, they're pushing their codes to be super efficient. But, you know, there are laws of diminishing returns for things. So, for instance, you can see on this graphic that the yellow line represents lighting power density. Lighting is one of those, used to be one of those low-hanging fruits that we could go and say, well, we can move from a T12 fluorescent or a metal halide type light and move it to something like a T5 light, or now an LED light. Well, now we've got the codes are almost to LED level lighting power densities. So, you know, there isn't a whole lot of lighting technology out there that's more efficient than an LED light. So we really kind of dropped the curve on that and hit the law of diminishing returns, where we're just not able to really get anything much more efficient. So, you know, same thing kind of goes with HVAC equipment. We're able to make some big jumps in efficiencies, but without some kind of major revolution in design of and manufacturing of equipment, there's only so much more efficient you can make the refrigeration cycle with the refrigerants and the types of equipment that we use today. So the building codes are projecting downward, and they're going to continue to project downward. They're not going to make the giant leaps that we've seen in the past 2 decades, but they're going to continue to project downward. But just because the code says you have to design to that standard and that zero energy level doesn't mean that buildings actually are going to perform that way. So we're going to talk later in this discussion about how important the actual construction and the operation of the building is, the commissioning, the measurement and verification, the keeping track of it. This is a graphic from the New Buildings Institute that went and did a study. Some of you have probably seen this. It's been around for quite a while now, but it did a study of buildings that applied for the LEED new construction program and were either certified silver or a gold platinum building. And it went and took the measured energy performance of that building versus what they had modeled it during design and plotted it on this graph. And you can see the the line at the top says they're saving more than expected. Some are saving less than expected. The 0% would basically be the baseline. So you can see quite a few of the buildings don't even meet the minimum baseline, and some of those are in gold, platinum, and silver levels. So just because you got a certification from a major institution doesn't mean the building's operating the way that it was designed to. As I mentioned, we're now calling these zero energy buildings. So we have a couple definitions here that come from the Department of Energy and NREL, the National Renewable Energy Labs. They published a document in 2015 that defined a zero energy building, campus, portfolio, and community. And they use kind of the same thing, where on a source energy basis, the actual amount of energy delivered is less than or equal to the on-site renewable exported energy. So the reason I bring this up is the discussion of, well, we want to produce more energy on-site than we have to take from the off-site sources. And off-site sources can vary. They can be a coal plant, a nuclear plant, a natural source from hydroelectric power. There's lots of different places, but they're off-site. It's produced somewhere else, and the emissions from that can be somewhere else. We can have emissions from all kinds of different polluting sources, and it's because we have that demand for energy on-site. But we start to see around the country, a lot of utilities, a lot of states are implementing higher percentages of renewables. And I see large solar panel fields when I drive, and everybody's seen the large wind farms popping up everywhere. These are high production, but it's not even a great fraction of the total energy that we're putting and needing from the grid to power our buildings today. I'm going to let Alan speak for just a moment.
Yeah, so I mean, generally from a zero energy perspective, here, especially from an on-site perspective, a lot of people talk about EUIs. You want a low EUIs, and you want some generations to be higher than you actually use. So the idea is you have generations higher than the usage, so you get to net zero. So that brings strategies to maximize our generations. But oftentimes that's limited to the location, type of buildings, weather. And another strategy is to cut energy usages, like on your in your building, to reduce load, to have some aggressive controls. Lot of the strategies. So from a design perspective, it's probably easier to do that, to reduce the load of your design, because from a generation perspective, it's too limited oftentimes. So it's probably easier to reduce load, to lower your usage in the building. So oftentimes we hear like passive designs. There is also certification about passive design. When we start designing a building, you consider like orientation. You do some natural ventilation, passive design. You have very high performance envelopes. Like sometimes people see like very high insulation levels. You see like solar chimneys. And for lighting today, Benny mentioned, LEDs, pretty much you see them everywhere. And plug loads, you can actually do like a lot of controls. You can shut them off. I think the energy code right now requires like a mandatory shut off for plug loads, which means if you're not using the building, if it's not occupied, supposedly some of the plug loads needs to be like completely shut off. So when you reduce the load, you have a smaller size of equipment, and you reduce usage. And from a equipment perspective, today, especially HVAC equipment, are very efficient, I would say. And you have a lot of different types of systems you can choose from. Probably like 10 years ago, you probably don't really see like rear F systems, but today in the US, you see them popping up everywhere. And you see like water to air heat pumps. You see, high efficiency chillers. So that's going to reduce our building usage as well. And also because a lot of certification program and also the energy code requires like not from a comfort perspective, but also from a energy efficiency perspective. They define a lot of daylighting controls. We oftentimes see like daylighting harvesting in office type of space. That's going to reduce a lot of lighting usage actually. And speaking of control strategies, in the past, some of the controls are like optional. But today, demand control ventilation, some shut off controls, some VFD controls, on the energy code, in a lot of cases, those are mandatory. Natural ventilation is a great passive design. And it not only, so it reduces consumption, but also at the same time, it brings comfort. And that brings us to renewable energy on-site generation. So you probably see like PV panels very often, especially if you're working on a net zero energy project. We don't really see a lot of wind turbines for buildings, but the most common option is solar PV panels. And sometimes we also see like solar hot water. It's different type. You're sitting on the roof, you have solar tubes, and that brings you hot water. And wind farms, those are expensive, but those are, some of the locations are great for wind energy. And we also have like some geo type of renewable. And like I mentioned, it's a little bit harder to maximize the options are sometimes are limited to maximize the generation. So that's why we spend probably more time on reducing the load and and also optimize our design. So then you bring the total predicted usage down, and then we can size the renewable requirement more comfortably, I would say. And that's generally the strategy here.
Yeah, I think that's a good overview, Alan, that if you can reduce the load of the building permanently, that's something that you'll be able to put a smaller piece of mechanical equipment in to handle that load as it is, and you can make that as energy efficient as possible. So you use as little energy as possible, keeping your renewables field as small as you can. Like Alan said, a lot of the strategies and efficiency as far as controls go, even with plug loads now, are mandated in the energy code that I was just talking about a minute ago. So a lot of the things that we have to do are starting to get built into practice just because it's code required. And lastly, just on the renewables that Alan overviewed, solar water heating we see most commonly on multifamily residential or single family residential type buildings because it works very well, and there's a lot more water consumption in those types of buildings. Hotels and places that dormitories that have lots of people and lots of hot water demand, those are good places for that type of system. An office building may not be the best use of that because hot water demand is very, very small. And on-site wind, I'll quote an engineer I've worked with at both Walgreens and with McDonald's, and he says, if you can find an on-site wind manufacturer that's going to stay in business by the time you build your project, they're probably decent, but their product probably won't work. So and that's been our experience on several projects with wind, especially in urban environments. We just don't produce very much, but it looks good, and it gives kind of that, on the projects we've done with wind, it's been more about the marketing to show that we're doing something renewable than it is about actually generating the energy. It's really the solar photovoltaics that are really taking off, and the efficiencies and the cost of solar photovoltaic has the efficiencies have gone way, way up from where they were 10 years ago, and the cost has gone way, way down. And so we're starting to see solar voltaic move into lots of different environments. All that said, we don't need to build buildings underground for them to be zero energy buildings. We still want them to breathe and live. We want them to be a comfortable place to go. When Alan's talking about all these controls, and different strategies and passive strategies, you still want to encourage comfort, especially now when we're looking at reoccupying office buildings and places like that. We're talking about increase in energy consumption in buildings to provide more and higher, better indoor air quality for, we're putting higher MERV filtration in, which is going to increase the amount of energy that we need to consume. We're talking about increasing ventilation, expanding economizer ranges, things that are consuming more and more energy at the cost of trying to provide a more comfortable and healthy environment within the office. So there's always a balance there, but the point is, we can make zero energy buildings, but we have to be really thoughtful about it.
So we mentioned like you need generations higher than the usage. And we actually probably spend more time on focusing on reducing, like to design a more efficient building. So, but here I'm going to talk about some considerations when you do the design. Generally, it's a little bit harder. The design is very dependent on, different locations. Generally, it's a little bit harder. If you're like in Chicago, you're trying to do net zeros, it's going to be harder than, you're trying to do that in California, in Arizona. The reason is because, so from a weather perspective, Chicago is really, really cold in winter. As you can see, it's in a 5A climate zone, and the big, the design heating temperature is at -10 Fahrenheit. But if you look at LA, so the design heating temp is at 43 Fahrenheit. That is significantly different. If you are in a heating dominant climate zone like Chicago, heating is your main consideration, I would say, and it's going to limit your options when you design HVAC system. It's also the reason why we don't really see many, people like to use heat pumps, right? Heat pumps, VRFs, because you have, you bring down the EUIs, but you're probably not going to see many air source type of heat pumps in Chicago. The reason is because it's too cold, and it's not going to, a lot of times it's not going to work. The most common heating option you see is going to be gas, I would say, gas. So rooftop unit, you have gas fire heating, and if you have office space, you probably have rooftop unit plus FEM hot box, VAV box, and sometimes you see like gas fire boilers sending hot water to those VAV boxes. And the reason why they use gas heating is because it's the availability and also the capability. We oftentimes talk about, a lot of designers mention, they want a all electrical type of design, and it's going to be a little bit hard in Chicago because the options are too limited, and geothermal sometimes could be the only option if you want. It's water to water type of heat pump, right? So it's probably the only option sometimes for all electric type of design. But at the same time, if we look at LA, the weather there is very mild, I would say. You don't really need a lot of heating, and you don't really need a lot of cooling. So if you like to use heat pumps, you can definitely use air source heat pumps, not just on space heating, but also on the water heater side. You can choose air source heat pumps. Then you don't have to use the water. And for water heating, you can use air to water heaters actually. That's very efficient, and that's why it's a little bit easier, from a design perspective, and especially HVAC perspective. You have a low EUI if the project is in LA. Also, there's another consideration about solar availability. Um, I'm also using Chicago and LA as example here. Here's a map generated by the National Renewable Energy Lab. It's the average solar irradiance map. As you can see here, if you're in Chicago, if you put up solar PV panels, average, you got like 3.72 kWh per square meters per day. That is how much you get from the solar. And if you're in LA, average you got 5.4. That is, I call it like significant difference. So we talk about generation and we talk about usage. So in Chicago, you have generally, if you have the same area of PV panels, same size of PV panels, you generate less. Also, at the same time, because of the weather, you use more. But if you're in LA, you generate more but at the same time because of the mild climate zone, and you use less. So that's why I would say it's easier to do net zeros in LA than Chicago.
I'd agree with that, but we joke in some groups about how difficult it is to build zero energy buildings in northern climates like this. And they just fall off of trucks in San Francisco. So it's, you see most examples when you go to, there's a great database I can share after the presentation here of registered zero energy buildings that are around the country. And you can kind of see where most of them live, and they do live in the more moderate climates and places with a lot of solar availability, but we can't make it happen here. And we've worked on a project at a school in northern Wisconsin, in Green Bay, that it's a tech college that actually trains people on how to be solar panel technicians. And they didn't have the resources to buy the solar panels when they built the buildings. They didn't have the funds for it. But we did the design in a way that was able to minimize the load and make it zero energy ready. And now they know exactly how much solar they have some operation, and they'll eventually put the solar panels on the building. So, as a good example, Alan said, there aren't a whole lot of buildings in the Chicagoland area outside of maybe a few residential and smaller buildings that are zero energy buildings currently. And we'll talk about one that we've worked on, just a few lessons learned from that. In Evanston, Illinois, we several years ago opened the Walgreens store. Many of you have seen and heard about this project, so we're not going to go into too much detail, but I'll kind of give some of the higher lessons learned about it. The project's won a technology award from ASHRAE. It's a very unique building beyond just being a zero energy building. It has a lot of other natural features and characteristics to it. The design really tries to accomplish the net zero, but it comes down to the little details that can really challenge a project, and they can be overlooked in construction. They can be overlooked in design. And I'll talk about one that's fairly commonplace in a lot of projects we work on. We really have to work with a lot of architects and contractors to make sure that everybody understands the importance of little tiny details. So here's a detail of a mullion on a curtain wall, and this was at the Walgreens project. And we saw this after the project was actually built and the glass was installed. In fact, the last pane of glass was being installed when I received these documents. And to the untrained eye, this looks just fine. When we put it in our 2D therm modeling software and look at the heat transfer of it, we see a problem. We see this little coloration that's kind of the green and blue colors coming through. What that is that's thermal energy conducting from outside into the space. And it's doing that because we're missing a gasket. It's called thermally broken glass. So there's no thermal break in this mullion. So the aluminum is continuously channeling energy from outside to inside. And you might say, okay, a little tiny rubber stopper at the end of this glass, costs virtually nothing. Very easy to install, very commonplace in the glazing system. Overlooked in this case. We have the as-designed properties of this glass, and this probably won't mean a whole lot, but I'll show you the importance of it. But we have the assembly of the glass. So that's the glass itself plus the framing system. Had a 0.41 assembly U value, which is pretty good. The code is higher than that, so this is better than code compliant glass. And you can see the center of the glass had a 0.32 U value, so that's just the glazing part of it. So the framing does make a difference. The framing is what brought this from 0.32 up to 0.41, and this is assumed as a thermally broken glass. What got built, and again, this may not seem that big a difference, but you see the assembly, the actual center of glass value went down. It got better. It went to 0.29, but our overall assembly of the glass went up to 0.46. Now, is that a big deal? Yes, it was a big deal. So in the summer, it's not as big a deal because we don't have that big a temperature difference from inside to outside. So conduction's not that big. So, if we're maintaining the store at 77 degrees Fahrenheit and we're at maybe 92, 95 degrees Fahrenheit outside, which I believe this August 25th date was a peak day. So it was about probably a 95-degree day. You can see there's a roughly 4% increase in energy, but it's still a 4% increase in energy. When we look at January 6th, which was a polar vortex day, and I believe this was like minus 10 to 12 degrees, somewhere in that range. So again, a design condition, as Alan pointed out earlier. You can see consistently we're pouring a tremendous amount of energy. The units on the left here are BTUs and British thermal units. So this here is about a 15% increase in energy. And, engineers don't necessarily always design for that. We'll go to that in just a minute. On top of that, things that we may think are actually an energy improvement can turn out to be a detriment. So with a high frequency building like a store, you have people constantly coming in and out. One of the discussions during design was, do we put an airlock in versus putting a revolving door? Well, the revolving door was a less expensive item, and we believed in discussions but there's no real scientific evidence or studies to show any different. We believe putting an airlock in would actually be more efficient because we wouldn't have as much air coming in from outside. Well, we still haven't done a research project on it, but I think the consensus here was the airlock the revolving door brought a tremendous amount of conduction and thermal energy, as well as direct infiltration in through. Even though it has seals on it, it could never be sealed up perfectly, and it just was a high conductor. It didn't have a lot of thermal break on it and provided a lot of thermal energy that we didn't expect. Additionally, little details like not putting a little bit of insulation around the slab edge can make a pretty tremendous difference. It constantly brings cold air or cold temperature in, and you get this. So the slab edge, part of the slab edge here wasn't thermally insulated against the outside, so it's constantly bringing cold energy into the space. So these are little details that can easily be overlooked or thought that they're insignificant, but they can make a pretty big impact to the design and operation of the building and the comfort of the occupants. This is a 10 kilowatt electric portable heater. And if you're trying to do a zero energy building, this is not something you really want to put in your space, but it was necessary while we tried to figure out how to get this building to warm up. And that was because we right-sized the equipment for the loads that we made based on assumptions that the slab edge was insulated, that the revolving door wouldn't have as much conduction and infiltration, and that we'd have thermally broken glass. So we didn't oversize this building's HVAC system, which I'll describe in just a moment. So as engineers, my first job, our rule was you oversize cooling by 15%, you oversize heating by 25%. That's how I was taught to design buildings and building systems. And there's a great study from quite a while ago that Kansas State University put out on how we overestimate plug loads in buildings and how overestimated our design of buildings are. And I remember I did a study back in the early 2000s on, I took a plug-in meter and went around to all the things in our office at that time, a computer screen, a PC computer, a printer, a fax machine. Yeah, we still had fax machines. And kind of took what the actual energy was and compared it to what we looked up when you go to an ASHRAE fundamentals handbook or a load sizing guideline. And even at that time, it was tremendously different. And a lot of people still designing to the fundamental guidelines because that's our standard of care. Well, we're oversizing our building systems tremendously. And when we oversize buildings, they operate less efficiently than a building that's right-sized. So, you want to try to balance the risk of operating. And there's also a resilience element to that as well, meaning, our climates are changing. We're having hotter summers, we're having colder winters, longer cold spells, and things of that nature. So we have to decide how we want to design our buildings for the future as well as today. Alan, do you want to?
Well, this is not directly about energy usage, but this is also a very important topic about resiliency. And you probably hear this term very often from a government type of project, from schools, from like town halls. So as we know, our climate is kind of shifting, as Benny mentioned, and some of you guys probably know, even ASHRAE is shifting the climate zones. So that brings another consideration when you design a building. You have to consider natural disasters. Here's a map from FEMA. In the past, 60 something years, all the natural, like the most claims of natural disasters. As you can see here, some of the states, they have severe storm, they have flood, they have hurricane, and also there is it doesn't show up here. Some of the states, they have hails, and luckily for us in Illinois and some, like the two locations I mentioned previously, Illinois and California, seems like natural disasters probably less than other states. And I did a competition type of project. It was for a government facility. And their requirement is to, their priority is actually resiliency. By, the term means if something happens, natural disaster, or like emergency power outage, the building can't operate for at least 2 weeks by itself. So that in that case, you have to design a very, very efficient system in the building, and also you have to design a battery system. So this building can still operate, they say 50% normally during that period of time. So I think as of today, this topic is gonna be more and more popular. You don't want to design a project, you put up a lot of solar PV panels on the roof, and that location, you have a lot of natural disasters. You have hails coming, you have severe storms coming. So yes, that's going to be, I personally feel like that's going to be more and more popular in terms of designing a building.
What I appreciate about some of the design in the UK is they have future prediction weather files. They've done research on what future weather patterns might be, and it allows engineers to model building energy at 50 years from now, what it might be. And I think that's something we don't really have here in the United States right now, and it would be a good place, and I hope a place that more research and work happens going forward. When we're designing systems, this is at the Walgreens project, for buildings, you want to generally make them very simple and easy for the operator, especially the type of operator. If you're a college campus, a healthcare campus, you're going to have extremely sophisticated engineers that understand the operation of buildings. You'll typically have somebody that is dedicated to just operating the controls of the building and can handle a more complicated system. I wouldn't associate that type of person with someone that works at a Walgreens store. So they're typically used to having a rooftop unit that someone comes and services every now and then. The project here goes back to the design. I'll give just a brief overview of it. As Alan mentioned, in the northern climates, most of our projects that go for zero energy strategies operate using ground source geo-exchange heat pumps. A lot of people call them geothermal heat pumps. I prefer to call it the correct name, which is geo-exchange. And we do that because the ground up here in the northern climates, typically around 55 degrees below 4 feet constantly. So that gives us a stable source of energy, energy exchange, as opposed to, as Alan mentioned, air source. When we fluctuate from -10 degrees to 95 degrees, over 100 degrees of temperature fluctuation in a season, air source has different efficiencies at all those ranges. So it can be a challenge to make sure that it works. With this project, what was fun was one of the challenges the engineers at Walgreens decided was they wanted to make it a all-natural refrigerant building. So I see my good friend John Malade has joined us today. Thanks, John, for coming. I know he's got the same feelings about this as I do. Refrigerants are a problem, and when we're going to looking at a typical heat pump, whether it's air source or water source, VRF especially, they still have ozone potential refrigerants in them that are causing environmental problems and not necessarily solving the problem. So we're not to a point yet where we're getting better energy efficiency. Yeah, we're using less refrigerant with smaller sized equipment, but to me, VRF is a very scary technology because it uses tremendous amounts of refrigerant compared to a smaller heat pump system. So there's something there that we throughout history, throughout mankind, we've sometimes solved problems by creating new problems. And I think I'm not saying VRF is that way. When we studied energy efficiency on this project and other projects, we found that actually a geo-coupled, a geo-exchange coupled VRF system can be one of the most outstanding performances from a coefficient of performance standpoint of any system I've ever seen. So back to the Walgreens here, we designed something that has never been designed or built before, and to my knowledge has never been designed and built since. They've had these machines similar to this, but they haven't had them coupled to ground source. So this is a transcritical CO2 triple temperature geo-exchange coupled heat pump. And what that means, the triple temperature means that we wanted to find a way to reduce loads. And when you have refrigeration, when you have any kind of refrigerators like a store does, grocery store or a Walgreens store would have, we have 50 foot of cooling and freezer cabinets in this store. And those are typically have a gas cooler on them. So they take the refrigerant outside and it relieves the heat energy that needs to go out. So it's always releasing heating energy 24 hours a day, 7 days a week. And we just felt we need to capture that energy somehow because we have a long heating season in Chicago and in the Chicagoland area. So we wanted to capture that and try to reuse it. And so we were trying to find some way to have some kind of heat exchange. And the only way we could figure it out was to throw it into the ground and use it through the geo-exchange. Through that, we stumbled upon the manufacture of transcritical, which is a refrigeration cycle process, which I won't put my glasses on and explain that cycle to you today, but if you're interested, give me a call. Transcritical is a process that we use with a lot of natural refrigerants, and CO2 is an all-natural refrigerant. And so we use this to keep any kind of HCFCs out of the building. And so the triple temperature means that we make chilled water, we make heating hot water, and we can relieve the energy off the refrigeration cabinets. all at the same time. So what I find still to this day extraordinarily fascinating about this machine is we make 165-degree hot water, which most heat pumps don't do anything more than 130 degrees, but because they have a refrigerant that's gonna blast off at 130 degrees, so you're kind of limited there. With all natural transcritical, we can go very, very high with the compressors, so we're not at relief. CO2 operates at a very high pressure compared to or I should say, a typical refrigeration unit that we use here in the United States. So it's somewhere around 80 bar, I think like 1600 PSI, somewhere in that range. It's a very high refrigerant pressure. So, but because of that, we're able to do a lot more. So this machine makes 165-degree heating hot water. It makes 30-degree chilled water, which is obviously below freezing, 30-degree Fahrenheit chilled water, and it makes one cabinet 32 degrees Fahrenheit for refrigeration and makes the other one -10 simultaneously, which I think is still a feat of amazement to me that something can do this all at one time. So it was a pretty cool machine, extraordinarily efficient. We didn't know actually what the coefficient of performance was going to be during design because nobody had ever built one of these. So we worked with some engineers in, I believe, Sweden to try to estimate what the efficiency was, and did a lot of modeling on it here in the United States to try to determine it. And it ended up being a very efficient machine with coefficients of performance that could approach 10. So that's pretty impressive in that realm. But it's a very complicated piece of equipment, definitely above the knowledge of most building engineers for operating, let alone someone that runs a Walgreens store. So I always go back to this statement. I always think as an engineer, we should kind of live by this motto, especially in my experience in working with operating buildings and commissioning buildings and working with people that have designed extraordinarily complicated control algorithms. Everything should be really as simple as possible, but it shouldn't be any simpler than that. I think that's a great statement of, if you want to make a zero energy building, back to that graphic about the lead projects that underperform, overpromise and underdeliver in that sense. Those types of projects really just prove too complicated either for the building operator or they just don't work the way that they were intended to work. They don't provide the same comfort levels. Things get overridden at the sake of comfort for energy efficiency, And it really starts with controls and overly complex control systems. I'm not a big fan of VAV or variable air volume systems. They've become the staple of office buildings and most buildings in the United States. And that's great, but they're moving air around. They seem like they're efficient, but there's much more efficient ways to handle building loads than moving large quantities of air and mixed volume. But the control strategies around VAV systems have gotten really, really complicated, and in our commissioning experience rarely work the way that they were intended to because they cause comfort issues. And so I think getting to the next level of energy efficient buildings, we're not going to be doing it through standard variable air volume design buildings. We need a much simpler controls approach to things. So I always like it we're working on a project in Orlando right now that's going to be a zero energy building, and we're looking at it, and again, it's a store where the operators aren't going to be sophisticated, trained engineers. They need to understand that we want the temperature and the thermostat set at this. We want to maintain control, and we want the natural ventilation louvers to open when the conditions are correct, but it all needs to be simple enough for someone to operate. We talk about lighting controls and how the code has mandated things, and they used to, everybody used to have occupancy sensors, and you'd be sitting there at your desk and the lights would go out and you have to wave your hand or get up and turn the lights back on. And we've kind of moved away from occupancy sensors to things that are vacancy sensors, which, you basically have to turn them on when you come in the room and they'll shut off on you. But, just telling people to shut off the lights works a lot too. I've seen plenty of buildings, and if you go any city, Chicago in particular, and you look at night and you'll see just large quantities of tall buildings with the lights on. And you just wonder how in this day and age, in the middle of the night with an empty building, especially now, completely empty office buildings, why are all these lights on? Why are things that are so simple so complex still? Alan kind of touched on this earlier, but we're getting kind of close to the end here. Alan, do you want to discuss just a few more of the passive strategies?
Sure. We mentioned that we probably spend more time on reducing the energy, and one of the very popular strategies are passive designs. So by passive design means you don't really um, use like actively mechanical system to reduce the load or so the focus is on, let's say, the orientation of the building. Are you facing south? Are you facing north? And what orientation brings you the lowest load? And also, and the opening of the windows and the doors. How do you bring like natural ventilation? So natural ventilation is one of the I would say probably the most popular passive strategies. How do you bring more natural air, outside air, without mechanical system to not only bring down the consumption of the building, but also bring to bring improve the thermal comfort. And so there are a lot of considerations can be done by the designers. It can be different height of the window, the size of the window, and the location of the window. And to be honest, I feel like oftentimes when people think about passive, um, the first thing they think about is insulation. Um, I mean, they tend to use very high, insulation like R50, R60, something like that. But I oftentimes I personally feel um, that is helpful, but not necessarily, um, those are expensive and not necessarily effective because, oftentimes we want to reduce the load. And if you actually do a load calculation, let's say from R30 to R40 or R50, you're not going to see significant difference. Sometimes it could be very, very minor. But if you spend more time, on the location, let's say location of the windows, if you could have like cross natural ventilation. So in shoulder months, you don't really have to use a mechanical system, but at the same time, you bring so much outside air and you feel very comfortable in the building. And if you also like the location and the size of the windows, let's say you can maximize your solar gain in heating season, but at the same time you can design like a shade system or overhang system that can block solar gains in summer. So overall, for passive strategies, I would say there are a lot of stuff can be done, um, and it's a lot of effort, but it's a great strategy.
So there's a couple slides left. We're coming up on the hour. So as I mentioned, commissioning is extraordinarily important, and commissioning is a process of validating that what was designed was actually built and operates the way that you want. When it comes to zero energy buildings, when we commission them, what we need to really pay attention to first and foremost is the energy consumption of things. And a lot of times we have to take into account metering and measurement protocols. There are often a lot of gaps in design because metering and measurement crosses trades and things kind of fall in between there. So during the design and into the construction, you have to be very careful to coordinate that all the trades are discussing who has what, that it's all been implemented correctly. Metering shouldn't be as complicated as it is, but it tends to prove to be one of the more difficult things that we have getting contractors to close out on and properly calibrate and have set up. But it's the most important thing in a zero energy building because we need to have that feedback loop on how things are performing. Now, obviously, in an actual environment, it's going to vary from what we have in a modeled environment. Our model uses a typical weather data file of 13 years from the 1990s, and every day our weather can change. I know the first winter that we opened the Walgreens store, our heating season was 16% more severe by average temperature than the model that we created. So we had to take the energy consumption that we were getting from the metering system on the building, plug it back into our model, use the actual weather to kind of see how we were performing, to make sure if any adjustments to sequences of operation, temperature set points, lighting, power levels, and things of that nature had to be adjusted. So there's quite a bit that needs to happen. Commissioning on a zero energy building is, in my opinion, one of the most important things. And lastly, the measurement and verification component of this is definitely one of the more important things. And, a lot of people don't advertise that they're doing a zero energy building. And I always think it's kind of a fear of failure thing where, well, let's try for zero energy, and if we don't get it, we just won't tell anybody. But I think as a design community, we all benefit from learning the mistakes or the things that didn't go as expected. And Walgreens at the time was extraordinarily helpful with that, because their intention was, we want to tell the whole world what we did wrong and where we went wrong, so that other people can learn from that, and we can get more of these zero energy buildings out and built. And I thought that was in fact, they had a mission statement around that project that said that very thing. So I thought that was very admirable of that corporate brand to have that take on sharing the lessons learned from it. And that's why we continually present that. I've got several net zero projects that we've done that we're not able to present on because they're not yet verified. I know the question was asked from John. I think he had to step out, but the Walgreens project has performed zero energy, and they have not, to my knowledge, publicized that through a certification program, but I believe they have publicized that. When we were last involved with it in 2015, it was operating 8 months of the year, where it was sending more energy out to the grid than it was pulling back in. Obviously, the winter months, especially with the way the envelope turned out, was a bit of an issue. But as I mentioned this, I'll quickly share one other thing. I mentioned at the very beginning of this presentation, the New Buildings Institute has this database that they've published of, net zero energy buildings that are emerging, that are basically in design, versus ones that have been verified. What we have here, I put up Wisconsin, Illinois, and Indiana, kind of the Chicago metro area. And this extends into Wisconsin and other parts of Indiana. But you see, there's only 20 projects that are in this database total. Only 2 have actually been verified, and most of them are still listed as emerging. And it goes to, I think, this fear of failure that people don't want to advertise. But I hope that more people take on the challenge of sharing their lessons learned and sharing their experience that they live through. So that is all we had to present today from a slide standpoint. I see just a few questions here in the chat window, so let me take a moment. As I mentioned, John's question, the Walgreens project has been zero energy, so that's been great. I see some conversation here around Tom's question. It's a good point. John put some good notes in the data about cost of a building. He works with a construction company, so he's got a good handle on it, and they do a lot of high performing zero energy type buildings as well. There is a cost. The Walgreens project had a cost that I was never made privy to, but I know the marketing and the sales in the store and those kind of things. I think the gist of it I heard was that they made up for whatever they spent on it and in the cost of it. It really comes down to how you design your building and how you take it up front. If you really plan to have it, you can minimize that cost because you can put smaller equipment in, you can have less energy cost. As far as a simple payback and things like that, it's really hard to say. Solar can be highly subsidized currently through incentives. So there's a lot of good things going on with solar and making it even more affordable to put on the buildings. Mr. Dwyer, thank you for joining. I think he had to step out here as well for another program, but he put some notes in here about the transcritical CO2 system. If you're really interested in learning about it, it is a very cool refrigeration cycle that does a lot of great things. We have a question here. Any story? Yeah, so I'll give a couple of answers. That's a great question about, is there a story about building maintenance to operate zero energy buildings? You know, what I've seen a lot of times is things get out of sequence, and they stop operating the way that they were intended to operate, and people don't notice it. We're starting to get more buildings putting in monitoring-based commissioning programs that are fault detection programs, essentially. So they notice when a valve isn't fully closed and it's leaking through, and they sense that the temperature is higher than it should be, or a VAV terminal box isn't working properly. These are extremely popular tools that are going to mostly commercial office buildings right now. In Chicago and the surrounding areas, ComEd incentivizes the installation of that software for the end users, so it's very popular. But as far as, you know, one anecdotal story, you know, we worked on a zero energy project where had a very efficient lighting control system. It had 8 different daylighting zones within the space that you tune those things at night. So you go at night and you get them to be the lowest lighting level that is comfortable, that the tenant wants to have. The tenants always want brighter, but in this case, we kept trying to push it down to get the energy down. We were using an LED lighting system, and so you do have to be aware that LED has lower limits and it has upper limits. So from 90% to 100% operation of an LED light, it's the same light output. So if you have a lighting system with LED lamps, especially any kind of fixture like that, you can start it running at 90%, because it's no different light level than it would be at 100%. Similarly, when you get down to 20%, down to 10%, what will happen with that kind of system is you can get into a flickering situation. So it can't just be a 0 to 100 control sequence with lighting. So in this case, we had taken it down to, I think, 65% in one area of the building to get the foot candles to where they wanted it, and we took it down to 40% of the light of the full output in another place, and we were able to get the lighting levels. Well, in a lot of buildings, the lighting controls are tied to alarm systems or life safety systems. And in this case, we had, it was tied to a security system that was a silent alarm. So when we had an employee of the company coming into the building, they were unlocking the building, and they were turning the alarm code off, but they were putting the wrong code in. And it was a silent alarm, so the lights would go to 100% like they would in a security situation, and nobody really noticed in the building. They were open it during daylight, and so it was just bright. Nobody really could tell, but the dimming stopped working because the alarm system was overriding it. And so this went on for a month, and we got the data, and we were doing an evaluation to calibrate it to our modeling system. And I actually have a cool graphic I left out of this, but it shows all of a sudden you see everything's following our model just perfectly, and then all of a sudden the lighting controls just go straight, and they're a straight line. And we couldn't figure out why this was going on, so we went out to the building and evaluated it, and we saw that all the lights were running at 100%. It was a user error, you know, but it was a maintenance issue that people hadn't realized this was happening. And so once we trained the operator and they realized what the proper code was to set the alarm into inactive, we were able to get that building back on track. Well, great. If you do have questions, Alan and I's emails are here. Feel free to reach out to us at any time. We will publish this on our website shortly, so the video will be up of the presentation and with the audio. So if there's something you wanted to go back and check on again, feel free to check that out or share with anybody. Again, we're here to help you. If you've got any projects that you're looking at, just let us know. We're more than happy to work with you on a zero energy project or answer your questions. Again, thank you for joining us today.